Okay. So MoEs increase the number of parameters for large models and decouple the scaling of the parameters with flops. They're also more sample efficient. So as we know, bigger models get to loss quicker. And one of the things that's underrated but sometimes mentioned is that they move towards adaptive computation. So in this picture, there's like n different experts, but there's kind of nothing to say that all these experts have to be identical. We could imagine a situation where expert N was like double the size of the other experts, and so the more difficult tokens get routed towards token N because it's more powerful or something like this. We could imagine this kind of situation. So yeah, that's kind of what's going on. And yeah, here's the picture from the switch transformers paper detailing out the same idea. So yeah, extension going into the straightforward layer which switches. Yeah. Any questions at this stage? Hopefully this is all good for everyone. Cool. Oops. Okay, and then so the problems with sparse MoEs. So a big one is they're not inherently fully differentiable. So if we look back at this, because we're switching between them, that's like a not necessarily differential. Oh, that's just some noise. Okay, great. Yeah, so in order to make it differentiable, so we can pass gradients back, we multiply through by the router probability to whatever comes out of the expert. And that helps us to really actually differentiate back through it. But like the operation itself isn't inherently differentiable, so that's one thing. Has discontinuity. So I think this is not always noticed, but so as we go through from one expert to another expert, so suppose you're traveling between the boundaries of experts, actually you're going to potentially have a discontinuous jump. So most things in neural networks are smooth functions. So if you're most things are linear, and then there's some activation. So Gelu is like everywhere differentiable. Relu is like piecewise linear, so it's certainly continuous. But with experts, we now have models that are not even continuous. So that's potentially a problem, and that can get even worse as you have more experts. You increase the number of discontinuities you have in your system. That's one thing. Another problem with sparse MoEs, routing algorithms are not generally GPU optimized, so sometimes there's some sorting involved or stuff like that. And what we want is like map mols and just basic matrix multiplications, which are really fast on GPUs, and sparse MoEs are not actually set up like that. Another thing, routing seems a little bit under optimized. So we have lots of different routing methods, so token choice, expert choice, some RL methods. However, all these methods they're better than hash routing, which is like a very basic approach where it's just like keep a big list of every input token and then say which expert is going to be routed to randomly. And all the more principled methods are better than hash routing, but only slightly better. So we'd kind of expect them to be a lot better. So that suggests kind of like we're not quite got the right routing mechanism yet. Still, we also have problems with token dropping. So if an expert is full by the time a token wants to come to it, then that token just can't go. So it gets dropped and we don't apply any parameters to it at that layer. Similarly, if an expert is not full enough, then we're just basically wasting GPU hours. We're not going to convert as quickly. So that's not great. So they're both token dropping. If if an expert is too full, expert imbalances, an expert's not full enough, we use auxiliary losses to solve for both of these, so we can like balance the experts and the tokens and that kind of thing. But these require more tuning, hyperparameters, just increased complexity. They're not sequence level deterministic is another thing. So the outputs depend on the batch we're routing there's a discrete mapping from tokens to experts, but tokens not just in the individual sequence, but across all the batches as well. So if you have a situation where you have batch size more than one, then the outputs do depend on the batch, not just the sequence. So that's not actually sequence level deterministic, which can cause some issues sometimes. And another one, if anyone has trained source memories, especially back when they were just coming out, they were very unstable to train. They're a bit better now, but they can sometimes just diverge, getting nans for no reason. So yeah, that's pretty annoying. They've just not quite been optimized as much as regular transformers have, so it can be a bit hacky sometimes. Yeah, probably because of the discontinuity, so they can diverge sometimes. Yeah, any questions about those problems? If they all make sense. Yeah, also feel free to jump in at literally any time if there's anything that um, you know isn't explained well enough, or you want to clarify, or questions you have. Yeah, please just jump in at any point. Amazing. So, okay, now we're going to introduce soft MoE paradigm. So, the intuition is instead of choosing K tokens to get to each expert, as we've done previously, we're instead going to um, give each expert S slots, where slots are linear combinations of tokens. So, each slot can have a bit of a lot each token from the sequence, and we're going to put those all together in a linear combination, smush them together into one slot, and each expert gets S of those slots and does the port back on that. And that is pretty much it. Everything else is the same. It's yeah, that's really the only change. It's really a very sort of targeted change that we've made, and it pretty much solves most of the problems we mentioned in the last slide, which is yeah, pretty great. So yeah, I'm going to go through this in more detail. So yeah, don't worry, so that's pretty quick. But before we get into the detail, you might be like, "Well, hold on a minute. Does this actually make sense? Can we just sum tokens together and hope we're going to get something meaningful out? Like that's kind of like a weird operation to try. Like, does it work?" Well, one thing you say, well, empirically, yes, it's in soft memory, like we can look at the results later, but like let's get some intuition around why this might work. So if we have CNNs, if anyone, yeah, I don't know how many people here just MLP or they've been missing for images and stuff like that. But average pooling in CNNs is effectively a way of combining tokens together, right? And it's very similar. You can imagine that's pretty similar, or in general, most convolutional operations. Similarly, in language models, we know that we can do linear combinations of word embeddings in like word to vec style math. So like you're probably all familiar with the classic king minus queen, or how'd it go again? Something like king, yeah, king plus queen minus woman or something like this. Anyway, it comes out as yeah, I forget the exact details, but yeah, we can do math with words and that and tokens. So that's kind of the idea. We can do that kind of thing. And similarly, if you think about a transformer, so the residual stream stays the same throughout the whole thing, and then we have branches which come out, which read from the residual stream, do some computation, and then add back to it. So it's all addition. Everything is addition all the way along. So there's some intuition that yeah, okay, adding to in a linear way does kind of make sense. Yeah, we can go into this in more detail if people are still skeptical. But also, yeah, I guess the equivalent we could just say like empirically it just seemed to work. Yeah, so to the actual operation itself, this is kind of the key diagram for the whole paradigm. So yeah, let me just go through this. So you're getting in tokens, so n tokens in this case, and the first thing you're gonna do to them is put them through a router. So this is like a learned router, which is like a gating mechanism. It's just a linear layer in general, and this is going to give you back what they call phi in the paper, which is the weighting logits or the routing logits. Um, and then you're going to use that softmax across the softmax across the column dimension, so that's across the sequence, and then you can put those into slots. And then so that's going to be dispatch rates with the softmax, and then you're going to combine those together to put them into slots. You're going to forward the experts on each of the slots. So each expert has some number of slots, S number of slots, and they're going to forward through. You can get out some outputs of the slots, and then you're going to use the same weighting logits, the same routing logits, softmax on the other direction on the rows to get the combined weight. and you're going to combine the slots back into tokens, right? So yeah, just to be clear, just to go over that again, tokens are going to come in, they're going to go through the routing layer, which is like a linear layer, which gives us routing logics. And then we're going to softmax that across the column dimension, which gives us slots. So it's going to be S slots, which are going to go in for each expert. Each expert's going to have a couple of slots. We're going to forward pass through the experts as normal, and then combine the slots back into the token positions where they should be by using the combine weight, which is softmaxed of those routing logics across the rows. Yeah, I know that's kind of the main thing going on here. So yes, any questions at this stage? Okay. Yeah, so in maths, what it looks like is we're getting in X, which is the inputs, by those routing logics. We're going to softmax apply that to get X tilde in this case, which is the slot. Put those through the experts. Put those through the experts right here, forward past the experts, and then you do the combined weights by taking softmax across the other dimension and apply that to the slot, the forwarded slots, which gets us back to the Y. So this is C is the combined weights, D is the dispatch weights. And yeah, just in code, this is JAX, but hopefully it should be pretty similar if people are working in PyTorch or TensorFlow, I guess. I don't know if anyone still works in TensorFlow. So you're going to get the logics, routing logics by combining X with phi. Um, then we're going to softmax along the sequence dimension to get the dispatch weights, softmax across the slot dimension, the expert slot dimension to get the combined weights. If you're doing some PyTorch, you can't do multiple axes in one go. So you're going to have to flatten and then do softmax and then rearrange back, but same principle. And then you're going to forward, sorry, you're going to combine to do the actual combination. So dispatch X to the slots like that to get the X's, forward pass through all the experts, the relevant expert for each input slot, and then combine the Y's back to from slots to get back into the tokens, and then return Y out. That's software relay. Yeah. So yeah, kind of explain that in a few ways with the picture, the math, and the code. So hopefully that's clear. But if anyone has any questions, please jump in.
So it does look like there's a question in the chat.
Oh, okay, cool. I don't think I can see the chat from where I am, but
So Evelyn M asked, how does this compare to multimodal transformer models such as AntMal?
sorry, can you ask the question one more time?
How does this compare to multimodal transformer models such as AntMal?
Oh, nice. Okay, I'm not actually familiar with Ant MAL particularly, but yeah, I guess the seems fairly different in that it's not multimodal necessarily. This is can be one mode. So it can be just purely text or purely images in their case, or it doesn't have to be multimodal at all. Yeah. The only thing that's happening is you're combining tokens together. So I know there are some modalities where it's like quite common to combine things. So like images, like it's obviously common to do smushing of tokens. But this case doesn't rely on it being any like multimodal or anything like that. It could just be some single mode. Does that answer your question? Okay, and we're going to take that as a yes. Oh, did that someone speak there? Oh no. Okay, cool. Um, yeah, and I'm going to sort of claim that um, soft MOEs are kind of just a generalization of what we've been doing up until now. So if you take a sparse model and you reduce it to having one expert, that's how you get a dense model out of it. So in other words, a sparse model is kind of just a generalization of a dense model. And in the same way, if you take a soft MOE, but put the dispatch softmax temperature to 0, then you would get out a sparse MOE, right? So you'd be pushing it towards a one hot distribution. Um, like a one hot vector, and then that would give you sort of switch transformer style sparse MOE. So in some way we can think about this as just doing like generalizing the previous paradigm, moving out in concentric circles. So sort of, yeah, sparse models are a special case of soft MOEs, dense models are a special case of sparse MOEs. Yeah, so this is kind of implies that soft MOEs are just kind of just more general, and which is pretty good in general. So it's not strictly that the most general thing always wins. Like MLPs are very general. We know that they can represent arbitrary functions, but being more general and being able to also apply more flops concurrently with good inductive biases is kind of what we're looking for in a good architecture. So I think in that sense, it seems like soft memories are at least principled and seem like correct as a good architecture choice. Okay, so then they give a bunch of results. So they're applying it to images at the first instance. So they're comparing it to previous sparse MOEs, so expert choice and token choice, as well as dense model. And you can see um, that, yeah, effectively they are outperforming quite significantly all three baselines. So whether that's the dense model, the tokens choice, or the expert choice, they're pretty substantially beating. Oh, did uh,
Khaled, please mute yourself.
Mute yourself.
Okay, cool. I just muted. Hello. Yeah. And similarly, fine tuning onwards, they also see that it outperforms as well. It seems to be getting slightly diminishing returns, but it's still outperforming at the end. And we expect diminishing returns as we get to larger and larger models, especially on ImageNet. So it seems pretty reasonable. Yeah, in particular, there's some labels in ImageNet which seem like they might not be correct. There might be some mistakes. So we're never going to get 100% on ImageNet. So diminishing returns are expected. But yeah, that is one thing to know. We are definitely seeing diminishing returns. And they also do some ablations. So they show that each individual part of the algorithm is necessary. So they move from having a dense version to routing everything with identity. So effectively sending the first token to the first expert, second token to the second expert. That's what they're calling the identity. And so that is a bit better. Then they do uniform mixing, which is like instead of doing the routing based on the routing logics or phi, as they call it, the router, they just send 1 over e if where e is the number of experts to each expert, effectively just send everything out uniformly, and that performs a bit better as well. But yeah, adding in the soft routing is just better. The learn dispatch and learn combine just yeah improves the performance pretty substantially. So that's cool to see. And they do a whole bunch more ablations as well in the paper. A lot of experiments. The whole paper is like 42 pages altogether. So if you're interested in this, yeah, feel free to read it. It's pretty thorough, I would say. Pretty interesting stuff. And yeah, so I also do some underrated points of the paper as well. So we have, as we're going into the router, we first do the softmax, right? So if you think about how the transformers are gonna work, we're gonna do softmax before that. But there's a bit of a potentially some problem because as we scale the embedding dimension, then the things coming into the router is going to approach one-hot vectors in the softmax. So yeah, we want to avoid that in general. So they apply sort of a scaling factor by doing just sort of standard L2 regularization and a learned scale parameter. But that helps so that they don't need to change hyperparameters every time they scale the hidden dimension. So that's not really a headline result, but pretty useful if you want to train this thing practically. Another thing they do is normally with MoEs, each expert is a full MLP, so meaning the up projection, the activation function, and then the down projection. They instead change the paradigm a little bit. So they keep the same up projection across all of the experts. And then the expert part, the switchable part, is the down projection. So this is, it helps because you need quite many parameters, right? Because, well, they need exactly half the number of parameters as they were going to, or roughly half the number of parameters they're going to. And yeah, so it helps with the training and reducing the memory footprint whilst retaining still pretty good performance. And then the third thing they do, so since we have these operating only across the sequence dimension, the batch, we don't have any information crossing across the batches, which is really good. We get sequence determinism back, so this is great. If anyone remembers before layer norm when we're using batch norm and it's causing all sorts of issues, yeah, this is pretty good, I would say. This is the layer norm paper if anyone wants to go read it. Okay, yeah, any questions about the results, the ablations, anything like that?
Nope, that was really clear.
Great, thanks. Again, and now the million-dollar question, what you've all been waiting for. Can we use this in Llama or GPT for our decoding models? And maybe the answer is potentially, but not yet. So yeah, it's an interesting one. So can we do a soft memory version of GPT? Not quite yet. So yeah, I'm just going to read this in full because I think it's pretty interesting. Oh, sorry, one question in the chat. Let me just answer that before we go into this part. Is the down projection different from the up projection or also across experts? Yeah, so so when you're doing an MLP in general, you're going to do so you're going to be in your hidden dimension layer, effectively, the size of the hidden dimension, maybe call it D, and then you're going to take a linear layer, which goes up, typically 4 times the amount in like GPTs. Some other models have different amounts, but yeah, basically you project up to a bigger dimension, and then you apply a nonlinearity in that big dimension, and then you project downwards, right? And the thing that they're doing here is they're fixing the same up projection across all the experts. And then they're going to apply different down dimensions. So the learned part, which is going to be the expert, as it were, is just the down projection. Yeah, oh, cool, thanks. I think there's another person typing in the chat, so I'll just wait for that question as well. Oh yeah, good question. So yeah, questions about how software memory helps us reduce the forward pass flops. So we come back to this picture. Okay, so it reduces the forward pass flop in the same way that a regular dense, a regular sparse memory does. So if you have a sparse MoE in general, in fact, let's go to the original sparse chart. Okay, you have a sparse MoE, then you have the same number of flops as you do. Yeah. If you have a sparse MoE, then you have the same number of flops as a regular dense model. So why is that? Because you're only going to one of the experts, not all of them. So you have more parameters than you have in the dense model, but you have the same number of flops. So effectively, you're not necessarily reducing the number of flops, but you're keeping it fixed while you increase the size of the model. And so, like relatively speaking, it's less flops for model size, right? And sparse MoE is like the same, and the reason why it's the same is because the number of slots is the thing that determines how many expert forward passes you're doing, and that we just set that to be less than the number that it would be if you did all of them. So you can pick that. That's a hyperparameter that you're able to choose, and you can set that as high or low as you want. But typically, you just set it at least lower so that it's cheaper than doing, a large model where you like apply all the experts. But yeah, it's a hyperparameter. Effectively, you can tune it however you want. Cool. Yeah, glad that helped. Okay. And okay, yeah, so we're talking about does this work for autoregressive models? But yeah, I'm just going to read this in full. I think it's pretty clear and pretty important. So they write in the current limitations section of the paper under autoregressive decoding. One of the key aspects of soft MoE consists in smartly merging all tokens in the input. So that's the smearing thing that's going on. This makes use of soft MoEs in autoregressive decoders difficult, since causality between past and future tokens has to be preserved during training. So typically, the way we think about this in GPTs or any autoregressive models is you can't see, you can't look ahead. So if you're trying to guess the next word, if any information passes from the next word to you, then it's pretty bad because you could cheat and you're not going to get that opportunity at test time. You're only going to get that in train time. So it's not useful for you to train like that. In other words, if the sentence is the cat sat on the mat and you are the word the, we don't want any information from Matt to come back to you, right? So that's why we use causal masks in attention layers. So they specifically just mask out anything that's in the future. So you can't cheat, you can't look ahead. So one question you might have is, well, could we do that here? And they say, well, one must be careful to not introduce any correlation between token and slot indices, since this would bias which token indices each expert is trained on. So I'll dive into a bit more depth on what that's saying, but effectively, we don't want to introduce too much correlation between these two things. So one thing we could do is okay, so yeah, there's kind of two ways of getting around this, two ways to get this to work. And you could use a causal mask and let every expert have a slot for every token position, right? Or we could use the causal mask and set an ordering for which expert has a slot for the next token coming up. So we could say that, for example, token 5, we need some slot which only sees tokens 1 to 5 and doesn't know about 6 and onwards. So we could set that to be like, okay, expert 5, you have a slot where you can't see any of the past, but you only see so you can't see any of the future, you only see token 5 in the past. We could do that. So that would be like a uniform thing, we just set it, or we could set that as randomly. So there will be a slot such that its information is only from whatever token number and the past and not seeing the future. That's something we could try. But yeah, these two approaches are not going to be promising, unfortunately. So yeah, remember this is the setup that we're looking at. And yeah, this is kind of the complex part. So yeah, feel free to please stop me if this is not clear, and we can go over this a bit more. But if we set every expert to have a slot for every position, then this is going to be computationally really expensive and just maybe intractable. So, and the reason for that is they out in the time complexity part. They don't quite tie the dots together, but we can do that here. So, assume the per token cost of each single expert is order big O of k. So then soft MoE layer is big O of M, N, P, D plus N, P, K, where M is the sequence length, N is the number of experts, P is the number of slots per expert, D is the number of, what's D? D is the hidden dimension. And yeah, N again is the number of experts, P again, number of slots, and K is the forward pass cost of each expert per token. So they typically choose P equals big O of N over K. So like the number of tokens over the number of slots, basically the number of tokens over the number of experts, effectively, right? But if we want to have a slot for every position, then we're going to have to set P as like be like M effectively, and then with that, it's going to reduce at that point to big O of M squared ND plus M NK, and recall that M NK is the cost of running an ensemble model. So effectively, remember K is the number is the forward pass cost per token, and so that's an N is the number of experts. So that's actually just like saying we run N full models, just all of them, and then do an ensemble at the end or something like this. And yeah, we don't do that in general because that's super compute intensive. Yeah, it would just be pretty hard to get that going. It reduced the whole point of Mischief Experts is that we can scale parameters without scaling compute, and this is saying we're going to scale parameters and compute like linearly together. So that's like not really what we want. So yeah, and in particular in their experiments, they show that soft MoE works best when num expert is the context length. So in other words, the slots per expert is 1, but we're saying it's actually going to be the context length. So we're gonna like basically square the number of slots required, which is this thing is going to be super expensive computationally if we try this. Oh, okay. Someone's asked how to derive the time complexity expression. Yeah, so actually we can probably do this. This is so hard. So this is basically the routing part. So you're routing M tokens to N experts, and each one has, this dimension. So this is how you're going to do the routing layer. Basically that map mole, and then all the stuff that goes around that. In the routing part. Yeah, and then this is the actual forward pass of the expert. So there's N experts. Each one takes K. That's this per token cost of a single expert going through, and there's P slots. So this is forward pass expert. This is do the routing to know which expert you should push each token to. And then you add that together to get the time complexity of the whole soft MoE layer. Yeah, feel free to keep the questions coming because this is like the most sort of complex part, I realize. I think someone's typing in the chat, so I'll just wait for that before we move on. Oh, yeah, sorry. So this part is the complexity of the routing layer. So actually doing the routing, that map mole, and just like pushing everything to the right place. So Again, M is the sequence length, N is the number of experts, P is the number of slots, and D is the hidden dimension, so the embedded dimension. So when you're doing that matrix multiplication, it's going to be we're going to doing the multiplication along those axes, and you can kind of work it out when it comes out as the time complexity is about that. And then this is the actually doing the forward pass of the expert. Yeah, in general, like we should expect that doing the forward pass is much more expensive than doing the routing. So this part should like go to be dominated and be pretty insignificant. So this is really the actual part that matters, I would say, if you're actually trying to calculate time complexity. And they kind of explain this part a bit here. Like it's going to be dominated generally. Oh, routing meaning like the gating mechanism, the linear layer, which is the routing, yeah. Probably that's my accent. Sorry about that. Cool. Okay. Yeah, and so sorry. We recall that there were two methods that we could get this to work. So one was have every expert to have a slot for every token position, and that's the one we just showed. Time complexity wise, is like not a great method. And then there's a second method, right? So that's use a causal mask and then set the ordering for which expert has the slot which is like doesn't see the future for each token. And you can do that in any kind of way you want, but that's the second approach, right? And so what's bad about that? So if we say, okay, expert 5 is going to look at position 5 and behind, then that means there's actually going to be a difference between if we see cat at position 5 versus cat at position 6. There's genuinely like it's mapping to a completely different expert. It's doing a completely different function. So we're basically overfitting to the token positions and as the slot positions, which introducing such a correlation between these that it's going to cause us real issues if we go down. That turns out that that's not great for us. And then we can also choose like random slots, so that kind of limits the issue of like overfitting, but it basically means the expert's not going to specialize. Each expert has to be able to deal with everything that comes. So effectively, all the experts are fully general, and we don't get any of the all the benefits of specialization, which is the whole point of redoing experts, right? The experts on a particular type of token, but they're not going to be experts anymore. They're going to be generalized, and they don't specialize. So this is also not great. So yeah, this is a bit annoying that we thought we had a good approach, and it seems like it's not really going to work with autoregressive models, at least not without a little bit of extra research. So yeah, not great. We thought we had something good, but it's going to be a little while until someone comes up with an approach that actually makes this work, I think. So yeah, getting soft MoE to work for decoding models is kind of an open problem that I think will be really cool when it's solved, if it's possible to be solved. But right now, there's a lot of teams working on this, but no one really has a solution as far as I'm aware. At least no one's published one. Software is pretty much a game changer for anywhere where there's an encoder. So translation problems, vision transformers as they show in the paper, audio, anything like that. And I know there's a lot of T5 haters out here, but T5 might be back maybe. But overall, software marine seems like a really cool approach for those kind of models. And here's the stuff I used coming up with this talk. I'll share the slides around afterwards. You can feel free to have a look at those links if you want. Yeah, that's pretty much all those things I had prepared. So any other questions would be cool to hear, especially questions about the autoregressive stuff that I'd be definitely very interested in understanding people's thoughts on that. Yeah, so soft MoE for encoders and token trace for decoders is kind of how I'm thinking about it currently. And yeah, what I'm encouraging people to do in their models. Yes, there's another question saying what happens in performance versus the equivalent dense model if we let every expert in the MoE activate. So it will be better. So every expert activating, so you can think about that as an ensemble effectively. So you're going to apply all the parameters to every expert, sorry, to every token. But you can also think like if you're going to do that, like why not just increase the hidden dimension or like significantly and just get more parameters that way? That is might be a question you might ask. There might be some benefits in terms of training stability and potentially sample efficiency, maybe like probably not huge. Yeah, it's like yeah, but also like the main point of MOEs in general is that you can increase the number of parameters without having to increase the compute. And if in the approach where you let every expert be activated, you're increasing parameters and increasing compute side by side, like they're just increasing together. So yeah, you kind of lose a lot of the reason you might have got into MOEs in the first place. So one question is, so soft MOEs don't really fix token dropping. The slots could all choose to ignore some token by assigning middle. Yeah, so that's technically true. So I think the problem with token dropping in general is that, like, so one problem with token dropping is that you might have a situation where a token actually wants to be assigned to an expert, and the expert wants to be assigned to the token, etc., that mutually wants it, but the expert is just full. So it gets dropped, even though it would have been benefited from going through the expert, and like everyone knew, the router knew that it was going to benefit from that. Um, so if the kind of token dropping that I believe you're talking about, Jason, is where like and a token just gets ignored, but that actually might be optimal. That's not necessarily bad. Like some tokens might just be very easy, and it's fine to ignore them. But they only need to get processed by some layers, not all of them. The mathematics agree that's optimal. And secondly, you can apply some sort of auxiliary losses to fix against this. Token socialism. Okay, yeah. If you want every token to have some to be processed, then yeah, we can use auxiliary losses to like balance tokens and experts and do some stuff like that. That's definitely possible. There's a bunch of papers which introduce different auxiliary losses to help this balancing process, and a lot of them seem to work. You know, kind of well. But yeah, I don't think token dropping is necessarily a bad thing. Like some tokens getting dropped so that other tokens can get processed more, I think is a good thing in general. Like being able to specialize on some tokens and like let tokens that don't matter go through. Yeah. All tokens are equal, but some tokens are more equal than others. I agree. I don't know if I missed any of the questions in the chat while I was talking about that. It's fast feed forwarding nice if you compare it side by side with soft MOE. Okay, so I actually haven't. I've read the fast feed forward paper. I haven't really thought about it super deeply. I only skimmed it, so I actually don't know the best person to answer this. Anyone else can come in on this. Anyone who's read fast feed forward that wants to come in on that's how you compare that to soft MOE. Yeah, feel free to just like unmute and speak up if anyone who's read that paper deeply. Okay, maybe no one's actually read the paper. Okay, so yeah, maybe I'll have a think about that and I'll try and get back to you. Buttercutter. Any other question? Yeah. Okay. Cool. I think that seems like pretty much everything. Yeah. Anybody has any other questions, please feel free to just raise them. But yeah, gonna stop sharing now. Yeah. Thanks for listening. Hopefully that mostly made sense. Yeah. Self-memory. I think it's a pretty encouraging approach.
When do you think the first replication of a soft MoE model will appear in the public?
In like a paper, do you mean, or?
Paper is fine as well, if you happen to be working on one.
Um, I'm not working on a paper with software right now, but so there's implementations in terms of if you're stuck thinking about looking at it. So Google has a JAX implementation available. Lisa James has a PyTorch one, and some other
Yep.
people. I have a PyTorch one, I think. But yeah, in terms of like replication on other domains, I guess is what you're asking. Yeah, I don't know.
Yeah, I guess it will have some potential work in audio at least.
Yeah, audio. I think audio would be super cool for it. I think it's like pretty much perfect for that use case. And yeah, also translation. I think that people should definitely try and use this. So yeah, for like encoder decoder sort of stuff. So I'm excited on seeing it, and I think it's probably coming sort of any month now. I would say any week now, I guess, realistically.
Short timelines.
Yeah, timelines. I don't know specific on timelines, but if anyone is working on this, please let me know. I'd be very interested to see it, and if you obviously share it in the the channel when you release your paper and all that. Yeah.
Sigas, do you have any plans to present a paper next week, or?
I don't know if anyone else wants to present something. So
Oh
next
no,
week,
cause SE guys or Sigas, I don't know how to pronounce his name. The previous week was giving a possibility to present a paper the next week. So I was trying to ask him, basically.
nice. Okay.
I'm probably still good for hash routing. I haven't actually written anything up yet, but I've read the paper, so I think I'm good for it.
The question is open to anyone else in the channel right now as well. If there's any paper about mixture of experts that you'd like to go through that we have not, or actually even if we have already gone through, then please do share in the either reading group chat or this voice channel chat, because more presenters is always good. Guess that's a no.
No, yeah, if SE wants to do the hash routing, that would be cool. Like, I know I'm touching on it very briefly, but I think hash routing is super interesting because it seems to work like surprisingly well, given that it's like such a dumb thing to try. So
I
yeah,
mean,
super
Exactly.
interesting.
the reason I decided to throw myself on volunteering for it is basically that I found myself bringing it up every third MoE related conversation. Be like,
Yeah.
well, this kind of shows that it doesn't matter though, because that's effectively the main takeaway.
Yeah, definitely. So I think my take on it and is also very underdeveloped. So someone might have a better take on this, but my take is that um, like there's enough space in the previous MLPs or linear layers in general to sort of arrange in such a way that they can like learn what the hash route is expecting, and then they can just basically do the work that a linear layer was going to do. And so they're like routing, effectively pushing the routing mechanism back into the previous MLP or the previous
Interesting.
linear layer.
Yeah, you get an extremely dumb routing mechanism, and that means that it either it's one of two things. It's some combination of the previous layer is doing the computation, or you're actually just dividing up, since your outputs are usually on a sphere or a cube. You're just dividing
Mm,
it, like straightforwardly, just dividing it into pieces and assigning it out.
yeah.
I honestly think if I were
Oh.
recommending it right now, I'd recommend soft on an encoder and hash on a decoder.
Yeah.
Oh, hash over token choice.
Yeah, because I don't.
Damn.
I think there's one token choice implementation that beats hash cleanly, and other things don't. But you have to deal with auxiliary losses and a bunch of other stuff. Whereas I kind of know hash is going to work.
Yeah, true. Did anyone record this lecture?
I think someone did.
Yeah,
I don't see it. Oh, okay. That's awesome. Yeah.
Yeah, no, thanks for recording, Phil. Yeah, that's great.
Yep. I guess we can end the call now.
Cool. Thanks, guys.
Later, everyone.
Later.